Okay, welcome. Good morning, good afternoon, good evening, wherever you are. Thanks for your attendance today. My name's Tom St.Onge. I'm Director of Operations at PRI Engineering, and I'll be the host for today's webinar. I expect quite a few more people or participants to join as we go through, but it's about time we get started, so we'll do that. Today's webinar focus is on solar foundation myths for cold climates. All right, there'll be a couple folks doing the majority of the speaking today. Myself to get started, and then I will hand the floor over to the COO of PRI Engineering, Arash Yazdani. Just a couple ground rules before we start. I'm going to leave the chat and the discussion window open. I would encourage you to use it. If you have questions or comments, post them there, please. You can also send me a direct message if you need to, and time permitting, we'll have an opportunity to potentially address some of those questions. If not, what we'll look to do is in the coming days, close with you, and through one of our social media platforms, we will post the answers to some of your questions. Okay, second point is just on recording. I am recording this through Zoom. It will be posted to our social media accounts on LinkedIn and Facebook in the coming days after some editing. And if you miss anything or you want to review something, I would encourage you to go to one of our sites and rewatch the video. Okay, I suspect there'll be something in it for you second pass through. Okay, we will get started. As mentioned, my name is Tom St.Onge. I'm the Director of Operations at PRI Engineering. Relatively new to the team. My background is in electrical engineering, and for a number of years, I was chugging along as a senior project manager for some EPC contracts. The primary speaker today is Arash Yazdani. He's the Chief Operations Officer for PRI Engineering. He is also the chief engineer for the company. So he is the technical authority for the work that happens at PRI Engineering. So a little bit about PRI Engineering. You can see here there's some impressive numbers. The team is quite experienced. We're growing. We have licensed engineers capable of operating throughout Canada and the United States. We've got a diverse background across different disciplines and lots of experience. From a project standpoint, the number is growing continually, and it's diverse again, ranging from preliminary studies to detailed design to construction support. The team's capable of supporting clients in many different aspects. PRI Engineering also has in-house laboratory capability, so we can provide material and performance testing for soil, aggregate, and concrete if required. And again, I can't emphasize this enough, but we are not geographically centered in one location. We do have experience across North America and the Caribbean. Today's webinar is going to cover a number of different things with the focus being on cold regions of North America. Arash is going to walk us through some theory and then some common foundation types. We're then going to dig into some case studies, and these are case studies from the very recent past, and we're going to explore and compare different foundation types as they were used in projects across North America. We're then going to wrap it up with some takeaways for everybody, and time permitting, we'll have some questions and answers if we can. Okay. With that being said, I'm going to hand the floor over to Arash.
Thank you very much, Tom. Thank you everybody for joining us today. We'll jump right into it. I wanted to start by setting the stage in terms of why is northern climates in North America unique to solar foundation design. So we'll start by talking about some of the primary design challenges. Starting with, in any cold regions, you're having to deal with frost uplift. Frost loading is 4 to 8 times greater than wind loading. And most importantly, frost is a long sustained load that acts over a long period of time, whereas wind is a short transient load. So if you think about it, when something is blown by a gust, there's a gust that blows and then it stops. It blows and then it stops, whereas frost acts for months upon months. The other big design challenge is that, compared to a conventional structure, solar arrays typically have a very, very large number of foundations. So a larger number of foundation elements results in a much greater risk associated with the construction of the foundation. Just as an example, one larger 600 megawatt site in Alberta, Canada had almost 250,000 foundation elements. The other big challenge is associated to the majority of the northern portion of North America is in what we call glacial till soils. And these soils are very high density and they have a high variability of gradation sizes, meaning they have anything from clay and silt particles, which you're unable to see with your naked eye, to large boulders the size of a Volkswagen Beetle. These soils are often very hard to penetrate, and they can come with a lot of surprises. So how do we manage that risk? We do so by doing a comprehensive foundation load testing program. This often, depending on the complexity of your soils, should be staged, should be completed in a pre-production phase, which would be looking at a number of foundation elements to gauge the performance of the different foundation types and also their constructability. You're looking for anomalies. The rule of thumb is that most solar farms, you're probably going to be able to get most of your foundations, 90% of them in readily. However, it's that final 10% that is always going to cause designers, contractors, installers, and developers grief. And back to these anomalies, the complexities, and the comprehensive design that go into these, and the number of foundation elements. One of the critical pieces is ensuring an adequate quality assurance and quality control program for the erection of these foundations. And then one thing that kind of goes back to the long sustained load versus the short duration transient load is that it's absolutely adamant that absolutely critical, that you assess the pile foundations for creep. Too many times we see designers that are used to designing primarily for wind uplift loads. They're only designing it for short duration loads, so they're not assessing the foundation for creep. So what is foundation creep? Essentially, that creep is assessing the foundation to see if that it has adequately sustained the load. And what you're doing is you're comparing the rate of movement versus time. So if the rate of movement is too high, however you haven't met the maximum allowable deflection, it's not appropriate to say that foundation has sustained that load. You need to continue that load until the creep has gone to a low enough threshold, or the foundation has deflected too much and it's considered a failure. Next slide, Tom. Okay, so common foundation types. The following 4 foundation types are the most common foundations used for solar farms. Driven piles, not just in northern regions, or actually I shouldn't say less used in northern regions, but definitely very applicable. If you're looking at solar foundations across the world in non-cold climates, probably about 90% of the sites, or maybe slightly less than that, would be utilizing driven piles. It is definitely the preferred foundation type. A lot of that is associated to cost of installation and cost of procurement. And also, a lot of the racking systems designed around the world are optimized for attachment to a driven foundation, specifically a driven W section. From that, we have a helical pile. I would say that this is one of the most common foundations used in cold climates. However, we're going to talk a little bit about some of the challenges with that. Some of the benefits, you can read out the torques, and you can correlate the torque to an uplift capacity based on pile load testing that's been done during the pre-production design phase. But one of the biggest challenges with helical piles is that seldomly can they penetrate into bedrock, and they have challenges penetrating into soils with large erratics, boulders, cobbles, and remember we talked about that, this is very should be expected in a glacial soil environment. The next foundation type that actually we design and utilize quite a bit in the northeastern portion of the United States is a ground screw. This is what I call kind of the silver bullet. It does have its challenges, of course, but it can be utilized in a very diverse subsurface conditions. It can be installed into soft sedimentary bedrock formations, and it also can be installed into bouldery, cobbly material. But with both those types of soil types and bedrock formations, it's not uncommon to require pre-drilling, which is another added step. Then finally, the most costly and what I would consider the most risky is a micropile. However, when installed properly and by a qualified contractor, it can be the most, it can come with the highest factor of safety. But, when we compare that to a driven foundation, for example, it's not uncommon for it to be 2 to 4 times the cost of that system. Next slide, Tom. Okay, so what do we got to consider when we are designing foundations in for racking systems? So we got to consider the geotechnical parameters. What is our predominant subsurface condition? What is the bedrock elevation? Is it 2 feet to bedrock? Is bedrock at surface, or is it 50 meters, 100 feet, 200 feet to bedrock? Is there a presence of cobbles or boulders? Do we have a groundwater table? These are all relevant factors which need to be considered into the foundation design. You got to do a foundation frost analysis. If you're in Canada, typically you will follow the recommendations of the Canadian Foundation Engineering Manual, which provides some good recommendations for using climatic data to determine frost uplift list, frost penetration depths regionally. In the United States, the U.S. Army Corps have some good guidelines for determining the same information. Both methodologies are very similar. It's somewhat statistical based, but there is just some minute differences between the two systems. We find that the U.S. Army Corps system is actually a little bit more conservative. However, it's obviously appropriate to be using the U.S. code or U.S. guidelines in the United States and the Canadian guidelines in Canada. We consider it paramount to do a pre-production pile load testing program. This is not only to determine the capacity of foundations, but also to determine the constructability of your different foundation elements. Remember, we talked about doing a pre-production testing program at the start of this for multiple foundation types. It's not uncommon, once you've determined the optimal foundation based on, 2 or 3 preferred foundations, what to do a second or third round of optimization, considering the preferred foundation only and doing a much greater number of tests. We also got to consider corrosion. So corrosion design in this aspect, in some cases could be atmospheric. However, particularly we're interested in the corrosion potential of the actual soils. And then we got to consider racking design considerations. So most, or not most, all racking suppliers, they will apply wind and snow loads to their system, and that will generate a top of pile load. From those top of pile loads, we'll be able to determine the cross-section size, and it's from the geotechnical parameters that we talked about earlier that we determine what's going on below grade. The racking design also needs to consider topography. Some systems have a much greater potential to traverse undulating terrains, others do not. Typically, if you have a highly undulating site, we highly recommend looking at a system that can work with that system instead of having to do a great cut and fill civil program, which not only adds risk from a stormwater management standpoint, but also adds very, very large costs to your civil construction aspects. Module bonding, I apologize, that's incorrect. That should actually say racking compatibility. So a lot of systems out there only can mate with a flat plate channel, such as a C channel or a W section. Some of the challenges associated with that is that you have to utilize in some cases, in these northern environments, it's much better to use a round shaft with a helical or a ground screw, and you need to kind of have a conversion kit, which often is designed by a third party to attach to the racking system. That adds some additional risk for the purchaser, because that could get you in some hot water for warranty, and also just adds another layer of complexity when you're doing your racking erection. Next slide, Tom.
I think you're kicking this back over to me.
Yes, that's on to you.
All right. All right, we did have some questions. I've seen some pop up. We will, I think, those are pretty good questions. We'll get to them towards the end. I just want to take the group here through a bit of a story and a case study. And instead of me just reading this slide, I'll tell you a little bit about this project in general and what my role was in it, and why this one is near and dear to my heart. So the case study that we're talking about here is W section versus driven round. But why this one matters to me is because for this particular project, I wasn't an employee of PRI Engineering. I was actually a client. And it was about 2 years ago when I was a project manager for this particular project, working for an EPC contractor in Summerside, PEI, so Atlantic Canada. Wonderful place. Go visit if you can. This particular project, it was in its infancy. We were in the planning stage, had kind of kicked off some initial design. And the advice I was getting as a project manager new to this type of project was that, we need to look at helical screw piles. And so I had started down the path of a helical screw pile testing program with a local contractor. To say it wasn't working is probably a bit of an understatement. A number of reasons for that. Might have been suitability of the contractor, had something to do with the ground and that type of technology, and really understanding. But the reality is I don't think I was getting the right advice. I was steered towards PRI Engineering, and it was about this time a couple of years ago when Arash and I had a real good initial chat, and he said, look, I think my team here can come up with a pre-production test program and design for you, but you need to trust me that it may not be what you think, and it may not be a helical. I said, okay, let's do it. And so PRI Engineering came up with a pre-production program for this particular project, and it consisted mainly of W section and driven round HSS. Okay, so that's what we were testing. The team deployed to the field, and what we were trying to do is determine suitability for both those foundation technologies, so that I could get a design and proceed through to procurement of the right rack. I mean, what we found was exactly what Arash would tell you, and probably against some of the normal understanding of these different types of technologies. What we found is the round HSS was a really good fit for this project site. There was some concerns with driven W section embedding into the weathered bedrock. We had much better success with the round pipe. Okay. And so in the end, at the end of the pre-production test program, we went ahead with a round pile design. Okay. And so this pre-production test program informed the design, which then informed my procurement activities. So went ahead through competitive procurement, sourced a round pile solution, and that's what we went forward with and installed. What did it do for constructability? Okay, because there's folks on here that probably care about some of these things. Well, constructability with a round pipe was quite good. Okay, the idea of warping and twisting is less of a concern with the round pipe. So if you ask the contractors on this site, they would say the round pipe was quite easy to work with. And so I saved time and I gained some advantage during pile installation activities. We went ahead and did a rigorous QA/QC program, concurrent to pile installation and at the completion. And we were able to adjust parameters as we go, and as the project went on through the 15,000 piles that we put in the ground, we were able to do it better and more precisely, which is exactly what you want. So we adjusted as the project went on. But I guess the million-dollar question is, okay, how do I know if all this investment up front worked? Okay, so it was not just budgetary investment, but time investment, engineering effort. Okay, how do I know if it worked? Well, for those that are aware, they would know there was a pretty good hurricane that ripped through Atlantic Canada last year. And it was just about the time that the racking installation and panel installation was completing on this particular project. And I'll tell you, it held up. And that's not a technical term, but the before and after for a hurricane-like situation directly on top of the project, our site held up. By comparison, there was another project similar in nature with a different foundation technology in the same region, and it didn't fare so well. Okay, so I'm not going to draw conclusions as to why. I can only tell you that for our project, we did execute and plan a deliberate testing program, and we made sure that when we chose a foundation and we chose a racking system, that it was informed by due diligence and informed by a deliberate approach. I'll leave it at that. That's the Sunbank Solar Project. It's wrapping up right now, and I think it's a great case study of why in this situation, driven round was superior to W section. And the proof is in the pudding. It held up. Arash, did you want to add anything on Sunbank? Okay, we'll keep going.
We lost the presentation, Tom.
Oh, we did. Okay, shoot. Let me get that back up. There we go. Can somebody give me a thumbs up that we got it back? Yep, good. All right.
Okay, I'll take over again here. So the next project we're going to look at is the Denos Solar Project. So The Denos Solar Project was a project that had been built in the 2015 timeline in St. Thomas, U.S. Virgin Islands. At the time, it was only about a 3 to 4 megawatt system. When Hurricane Irma came through the region, it devastated the site. And I visited the site. I saw the carnage. I actually we were scuba diving, or not, sorry, snorkeling off the coast one day, and we saw a number of solar panels in the ocean. So the debris stretched far and wide across the island. That those modules maybe were from the site. They could have been from other locations on the island. But nonetheless, the initial design was a very, very shallow ground screw. And, we only were provided anecdotal evidence of what happened during construction initially. And, while we are the believers that the foundation design itself was sound, but one of the issues was an adequate quality assurance and quality control program was not completed. There was a lot of stories, once again anecdotal, that suggested that proper care and consideration into ensuring the foundation was adequately erected was not present at the site. And in a lot of cases, the entire racking systems, we actually saw a lot of these debris in nearby fields, in the neighboring forested area, where the whole racking system, foundation at all, had been ripped out of the ground, which suggested that in a lot of cases the failure of this system was associated with the failure of the ground screw. And our hypothesis is that in a lot of cases they were having to do pre-drilling, and when they were pre-drilling, they were just focusing on getting the ground screw in the ground. And in a lot of cases, the foundations that went into the ground were going into disturbed soils for a number of reasons. It could be groundwater, it could be surface water, it could be, over drilling of the holes. We do understand they were adding some aggregate to the pre-drilled holes to potentially stiffen up the layer. But the problem with that approach is that you're disturbing competent soil. The soils at the site were very, very dense. High set, very, very soft bedrock, but soft bedrock is like a very, very dense soil, overlain by a dense to very dense soil. So we reviewed the geotechnical report, and actually from the learnings at another project, which I'm going to talk about next, we kind of saw some of the same geological conditions that we were seeing at this project in Alberta. And so that's why we suggested the driven round post. We did a full driven round post pre-production campaign where we tested about 30 foundations. And from that, we were able to design a final foundation. During construction, we did a full quality assurance, quality control program, and there was areas where some of the bedrock was too hard and we were not able to penetrate it. And in a lot of those cases, we did have to utilize concrete foundations. However, that was less than that 10%. And going back to what I had noted previously is that most foundations should work for about 90% of the site. So the risk that we're trying to always mitigate is that final 10%. So in this case, we were successful in doing so. We did have a successful project. The installation was completed, and racking and electrification of the site is now been complete. and the site is operational. So that was another example where the driven foundation was used in a case where there was, very similar to Sunbank, which Tom talked about, dense soils overlying soft bedrock. And within those soils, there was large obstructions, cobbles, boulders, anything from the size of my fist to the size of my head to the size of, a basketball or a large beach ball. The difference between a round post and a W section is that if you picture a W section, it's a point, and it's driving in the ground, and a point, as soon as it hits a hard surface or a large obstruction, it's going to stop dead in its tracks. But what happens with a round post, you have a round member that's hollow in the center. As that hollow member fills in the center with dense soils and bedrock, it goes from a closed-ended pile, an open-ended foundation to a closed-ended foundation. And that closed-ended foundation is able to shed obstructions a lot more effectively. It pushes them out of the way. It's not guaranteed. And in those cases where I mentioned where we had to end up doing a micropile or a concreted solution at this site, that would have been because the obstruction was just too large for that cross section to shed. However, compared to a W section, it's a lot more successful at doing so. And then, once again, we talked about the pre-drilling and the disturbance the ground screw did. In this case, we were able to drive the foundations without doing any pre-drilling, which allowed us to utilize the internal existing strength of the soil without disturbing it. And that's one of the keys here. Is too many times we see that racking suppliers say that you have to use a W section, or you have to use a ground screw, or you have to use this type of foundation. And what they try to do is they try to alter the subsurface conditions to meet the requirements of their foundation. A foundation is a man-made piece of steel. We have the luxury of making that and forming that to whatever shape or orientation we like. But geology is not man-made. It's put there by natural occurring events, natural occurring processes, which span millions and billions of years. So we don't have the luxury of altering those situations, and we need to work in unison with them. We have a slogan at PRI Engineering is "Let the ground do the talking." You have to minimize the disturbance of the subsurface conditions and match your foundation with what your site throws at you. Next slide, Tom. Okay, so the last case study we're going to talk about is the Montana Solar Project. So Montana Solar Project is actually the first place we looked at penetrating soft bedrock with a round-driven post. We were brought in late stages of the project. The customer, GP Joule, had been working with a local helical supplier, very similar to the condition and scenario that Tom had outlined at Sunbank, where the supplier was adamant that a helical pile can penetrate into this layer. They came out and they did a total of 27 helical probes. So what a helical probe is you're virtually determining the depth torque profile of the soil. So that tells us roughly what is the density of the soil. But it also tells us a little bit about the constructability. So out of those 27 helical probes, 9 of them did not encounter the required embedment depth. So that's 1/3. So 33% of the foundations would have not met that design requirement. So back to our 10% rule, that greatly exceeds that, meaning that there would have been a very high remediation cost, which would have likely associated in a large incurred cost to the EPC contractor, depending on how that contract was set up, or a large change order to the owner or developer. Neither of which is a good situation. So we wanted to come up with a solution that brought that 33 failure remediation rate down closer in line with about 10%. So we didn't have the luxury here of doing a pre-production test. So admittedly, as an engineer, I rolled dice, which as an engineer, we don't often like to do. But we made the assumption that based on the engineering properties that was presented in the initial geotechnical investigation report for this site, that the site could be penetrated by a round-driven post. Lo and behold, our hypothesis was correct. We went out and did a preliminary pilot program after only doing a quarter of the procurement of the site to get the project moving forward, but also to ensure that the technology we were proposing was feasible. And of course, thankfully, the project, the initial testing we did as a production testing program. So we installed foundations in random locations around the site in production locations, but we did pull testing on them to the pre-production load. So just for anybody that isn't familiar, typically when you do production testing, you want it to be non-destructive testing. So you would not pull test it to a very to the design loads, which typically includes some level of factor of safety. Typically, you would do it to a service load, meaning it's a much lesser load because you don't want to damage the foundations, because these are going to be used for supporting the racking system in the long term. Because of the background of the project, in this case, we did pull those initial foundations to pre-production loads, to the full design load, and we're very, very satisfied with the results. So the contractor ended up actually reducing the embedment depth a little bit from the initial order and ordered the remainder of the site. Of the 818 foundations, only 53 required remediation. And the remediation involved utilizing a PVC frost sleeve, which essentially reduces the frost uplift in the foundation. And that was done on 52 of the foundations. One of them was insulated, and the only reason for that is because it was racked. The racking was installed prior to the remediation team being able to put the sleeve on it. But the key here is that all foundations met the minimum embedment requirement, meaning that we didn't have any major constructability issues. It's quite normal to expect to see anomalies where the soil might be slightly softer compared to the site at large. So the 53 out of 818 remediations was considered a very, very large success, and this right here was not only the first application of utilizing this technology for us. It led to providing that recommendation to Sunbank and Dano and other projects that we've worked on since then. But it was also the highest success rate of a foundation meeting installation requirements. Back to you, Tom.
Thanks. All right. So we've walked through 3 case studies now, different situations, different regions, different, well, I would argue similar solutions, but all as a result of a deliberate program, right? And I think that's the important takeaway here. So for everybody on the line, I try to boil this down to a couple of things that I think are useful takeaways for the group. And the first is, and this was the trap I fell into as a project manager, was that helical screw piles are not the only way. You may get told that, you may get sold that, but there are other options. And as Arash alluded to multiple times, it's really important to let the ground do the talking. Second point is making sure that an understanding informs the design, all right? And you don't and you don't jump to a conclusion or make an assumption that will then in turn cause problems down the road. So understanding the subsurface conditions, understanding the geology, that needs to be the way in which you inform your foundation design. This next little bit is just me trying to summarize in a couple snappy words what I think is the right approach from a project standpoint. So plan, prepare, and then execute. So what do I mean by that? Well, you have to plan out your deliberate testing program, plan out your activities in such a way that you can engage the right team, develop the right program, and then prepare for it, okay? Prepare, give yourself enough time to execute the program, give yourself enough time to, and your team to analyze results and make good decisions. Make good decisions with respect to your design, make good decisions with respect to your procurement activities, okay? That it all counts. And then execute, all right? You don't want to get caught in a situation where you've decided to act first, maybe because of a schedule crunch, and then you're stuck reacting and remediating, okay? So do things deliberately up front and it will be faster on the back end. And finally, and this is probably the most important for everybody, regardless of whether you're here for technical reasons or you're here as a developer, you're here as a just an interested party. My lesson learned as a project manager, and now what I see through repetitive projects with PRI Engineering, is that a deliberate testing and design will mitigate risk. It's not going to eliminate it. There's nothing that will, but you will mitigate risks, especially subsurface risks that are unknown. You will improve construction, guaranteed. You'll create savings. And then probably if I had to add one more, because I'm just thinking about it, that you will improve quality, okay? So, in a nutshell, the purpose of this webinar was to kind of discuss northern climates and the considerations with respect to solar foundations. But we've kind of told you a story that spans multiple regions, and with the underlying thread that, every site is going to be a little bit different. All of the considerations are not going to be the same at every single project or every single site. And therefore, a deliberate approach is the way to go. And that's it. We do have a little bit of time. I promised I would, if we could, carve out a little bit. And I think, Arash, I'm going to throw you a lob ball over the plate here from the chat room. But I would like to just go back to something you said in a question that came up earlier about just uplift from freezing. There's a question, and I know we're speaking generically here from T. Madden, and he's asking how far in the south into the United States generally is uplift from freezing an issue.
Yeah, it's a great question, T. Madden. I can put. I'm going to put a map of the United States, which shows your frost depths in the chat for everybody's reference. I'd consider that a good reference, but on the eastern seaboard, probably down to about Maryland. Definitely needs to be considered up into the Midwest, and then the Pacific Northwest, not as much. Like Washington State, Oregon, obviously doesn't really need to be considered, in California. But where I would say this is most critical is in the Northeast and like the upper Midwest, Chicago, Wisconsin. If you want to, Michigan's not really the Midwest, but obviously a little bit of a transition between the Northeast and the Midwest. Those are your largest areas of concern. It definitely should be looked at in kind of that center band, lower Midwest, Maryland. I would say kind of south of Pennsylvania area, particularly in softer soils. If you recall looking at the glaciation map of North America, the glaciation line kind of ends in and around Ohio, halfway down Ohio, and most of New York State is within that glaciation zone. So that is the high risk areas, and that's where, into Vermont and Maine and upstate New York, where you're going to see, very similar frost penetration depths as you would see in Canada. And as you work further down, it's obviously becomes less of a risk. Hopefully that answered your question. If you got any other follow-ups, please feel free to put them in the chat.
Sure. Arash, there's a couple more in the chat. I mean, you can see them. I'm not sure if you want to tackle them now, or we can roll it up and send out some follow-up after the fact.
Yeah, no, absolutely. We can keep going down. So I see, do you consider adfreeze forces with moist clay, silt soils, but deeper groundwater? So that's an interesting question. So this brings up a very, 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 very big misconception in the world of frost design. There's a misconception, very, very large misconception in this industry, that adfreeze pressure and frost susceptibility are the same thing. And in fact, they are completely separate. Frost penetration depth is a function of the soil composition's ability to pass thermal energy. In this case, cold air will pass through coarser materials, sands and gravels, more readily than silts and clays, fine soils. Okay. When you're dealing with adfreeze pressure, the sands and gravels have a higher adfreeze potential, but they're better draining. And without the presence of water, which I think is kind of where your question was going, you're not going to have adfreeze pressure. However, I think, as you're also alluding to, if you have a moist clay and silt, it's going to contain water. The most frost susceptible soil is a silt because it's most susceptible to frost lensing. So throwing a lot of stuff here at you, but I hope this kind of allows everyone to appreciate, a lot of people think that if you eliminate the frost susceptible soils and replace them with clean sand, you've eliminated the issue. That is completely incorrect. Completely incorrect. And it's actually a major flaw in a lot of designs I see coming from southern regions of North America, where designers don't understand frost. What you're actually doing, like, let's take upstate New York, where I've seen this a lot. You're creating what we call the bathtub effect. So you've got fine-grained soils that are poor draining. They drill out those fine-grained soils in the frost depth down to 4 feet, and they replace it with clean sand. I've removed the frost susceptible soils. I've replaced it with a non-frost susceptible soil. Good to go. Incorrect. You've actually made the condition worse because you're creating a preferential flow path for water to drain into the pores of that sand. And then because the water goes into the pores of that sand, and it's poorly draining, the water sits there and it freezes and thaws. And so this is most largely an issue around that March, April time, in the spring thaw. Snow's melting. Keeping in mind, we said that thermal resistivity is higher in, is it higher? Well, it allows temperature to penetrate it greater in coarser materials, meaning that that sand that you've now replaced that silty sand with allows frost penetration to happen greater. So what's happening in the day when you have temperatures above freezing, above 32 degrees Fahrenheit or 0 degrees Celsius, water melts and then it goes into those sand pores. And then at night, the temperatures go below freezing again, and it promotes high expansion. That is what led to a lot of failures in Ontario of solar racking foundations. And so that's a large misconception. Mr. Schubert, it's a very comprehensive problem, and one that's very difficult to kind of answer in a couple minutes. But the big takeaway here is that frost susceptibility, add freeze pressure, and frost penetration depth are three independent soil properties which all need to be considered when looking at the potential for frost uplift. And so to answer your question, when you look at the potential, you got to look at total penetration depth, which when we're assessing a site, we do look at the soil types. That's why that initial geotechnical investigation is very, very important for determining the frost penetration depth. We then need to look at the add freeze pressures that would be generated from that. And then we also need to look at the availability of water, but that one you need to respect and appreciate that you're just taking information on a snapshot of time. That moisture condition could change. That deeper groundwater table could rise. You could alter the site and create a perch groundwater table, which is what you're doing when you create that bathtub effect. If you got any follow-up questions, please feel free to reach out.
Thanks, Arash.
Go ahead, Dom.
Maybe we'll just go with one more question before we wrap it up. And this will be, I'm going to fire it at you because I think it's a neat one. It's not necessarily a technical one and more of a commercial project type question. And it came from LinkedIn. I'm not sure exactly who's asking it here, but it's about balancing the project requirements, either from the client or the developer in terms of expertise and equipment versus what design you might think is best. So how do you blend the two? How do you bring together a client and or a developer need, want, ask, and blend that with your expertise and understanding it and design process?
Excellent question. And I can ramble on for hours about the technical merits and the technical requirements of undertaking a good testing program, but if there isn't buy-in from the developer, there's no point me even starting. So how do you balance that? Well, as an engineer, my duty is to only report on facts. I present the information. I need to do it in a way that hopefully I can, get that across to somebody that isn't a geotechnical engineer. Maybe they're an electrical engineer. Maybe they're a finance person. Maybe they're a project manager. So it's my job to provide them the information as it relates to risk, and that all comes back to cost. Remember I said, we always want to kind of be at that 10%. So I'll present, okay, here's your project risks. And, my original engineering mentor told me, every time you look at a site, you got to find that one risk with the subsurface. There's always one that you need to consider. And if you haven't found it, you got to go back and find it because you've missed it. So you got to present it from a risk factor, and then you got to associate that with a price tag. Hey, if you go ahead and do this thing, which I think is completely wrong from a technology standpoint, these are the implications. These are the resulting costs that you're going to incur. Are you ready? Some developers say yes. Some of them don't understand the implications truly and are just saying, we want the cheapest solution. And, I'm talking to a racking company and they tell me this is going to work and they guarantee this is going to work. And with all due respects to any of the salespeople in the crowd, a lot of times they're being sold a used car by somebody that unfortunately should not be selling them that used car. So, all we can do is present the risks. And if they take the bait, they bite on the information and they understand, quite similar to how Tom did. All I could do to him is tell him, you want to try a helical foundation in a soft sedimentary bedrock environment? I think you're crazy, but go for it. And sorry, Tom, to, he did try, and they had 3 days of helical probing planned, and they pulled the plug at day one when exactly what I said would happen happened. Thankfully for their case, they did that in a pre-production setting, not in a production setting. Could you imagine what would have happened if they went and ordered 5,000-6,000 foundation elements? on the basis of what that supplier had told them. So, you know, you just got to go back to the facts. And some people aren't a big fan of presenting hard facts, but you know, I tell all the engineers that work underneath me, the ground isn't going to change tomorrow, next week, or in a month. You need to present this in a way that is associated to the risks.
Great answer. Great answer. And I appreciate you using me as a punching bag. Good with it. But anyways, look, I think we're running short on time here. I just want to take a couple minutes and wrap it up. First and foremost, thanks for attending today. This one's been planned for a while. I hope if you're sitting here for the last hour, you took something away. The topic was focused on cold climates, but we went all over the place, and I think it was useful. All right. So regardless of what role you're in, whether it be a technical role, a project role, or a commercial role, I think there was something in this webinar for you today. So I'm interested to hear feedback and would love some feedback on this webinar. Next thing, I mentioned it at the beginning, but I'll say it again. We will make an effort to get this onto our socials, LinkedIn, Facebook, Instagram, as soon as we can. And after some editing hours, I'm sure it'll be ready to go. If you didn't get the chance to catch the whole thing, or you think this would be useful to somebody else that you know, please forward it on. Again, the more information we can get out there about these topics and about PRI engineering, the better. And finally, reach out. Okay, so you can see on the screen here now, there is contact information for our offices. We have 3 of them: head office in Lindsay, Ontario. We have a satellite office in Mississauga, Ontario, and as well a team in Calgary, Alberta. There is email address, there is a website, and there is a toll-free phone number. I will also ensure that I catch feedback and the discussion from the forum here, and we close the loop where and when we can. So that's it for me. Arash, over to you for any final comments, and then we'll close out. Thank you.
No, that's all. I mean, just you know, the inspiration for this webinar was truly because, unfortunately, I feel like there's a lot of misinformation going around in the industry that helicals are the beyond and end all. And, you know, while they definitely serve as a very, very useful vehicle for you know, supporting or resisting frost loads, in some cases, they actually can provide you with greater risk. So make sure you let the ground do the talking.
Thanks, everyone. Take care. Have a great Tuesday.